Welcome to the second lecture in the last week of our course Analysis of a Complex Kind. Today we'll learn about a special type of series, namely the power series. A power series, also often called a Taylor series, centered at a point z0 in the complex plane, is a series of the form sum k from 0 to infinity, ak times z minus z0 to the k. So z0 is this fixed number, and z is something arbitrary we can plug in there, so we can therefore vary this z right here. We've already seen a few examples of power series. For example, last class we looked at this series z to the k, and we found out that it converges as long as you plug in a z whose absolute value is less than 1. So in our power series notation, there's just a 1 here for the coefficient ak, so the ak's are all equal to 1, and this z0 is simply not there, so z0 is equal to 0. Here's another example. The series minus 1 to the k over 2 to the k times z to the 2k. So this series only has even powers of z, so all the odd coefficients are equal to 0. ak is equal to 0 if k is odd, and the even coefficients of the form a2k are equal to minus 1 to the k divided by 2 to the k. And we have z0 is equal to 0 again. How can we find out where the series converges? We can actually rewrite the series a bit by pulling out the exponent k out of all of these individual terms, thereby finding the series equals minus z squared over 2 quantity to the kth power. Because if I brought the k back in, that would be back to the left-hand side. Now, if I call this entire term in parentheses w, I get a series of w to the k, which I completely understand already. I know that series of the w to the k's converges when w is less than 1 in absolute value, and it diverges when w is greater than or equal to 1. What does that mean in terms of z? Well, the absolute value of w is the absolute value of minus z squared divided by 2. When is that less than 1? Well, that is less than 1 when the absolute value of z squared is less than 2. The negative sign goes away in the absolute value, and I multiply it through by 2. When is the absolute value of z squared less than 2? Well, that's the case when the absolute value of z is less than the square root of 2. And so we know that this original series, converges when the absolute value of z is less than 2, and it diverges when the absolute value of z is greater than or equal to 2. So how do I find out in general for a given power series for what values of z it converges? There's a following theorem. Suppose I'm given a power series. Then there exists a number r, and this r is between 0 and infinity. Infinity is allowable as a number r, and 0 is as well, such that this series converges absolutely as long as z minus z0 is less than r in absolute value, and it diverges when z minus z0 is bigger than r in absolute value. Remember what absolute convergence meant? That means if I put absolute values around all the terms of the series, then the series still converges. We noticed that absolute convergence implies regular convergence, but the reverse is not necessarily true. Furthermore, the convergence is uniform in the absolute value of z minus z0 less than or equal to r for each r that's less than uppercase r. Uniform convergence means that if I plug in different values of z's, the convergence is kind of equally fast. We won't go into details here. So here's a little picture that hopefully helps in understanding this theorem. This theorem predicts the existence of this radius r, such that in the disk of radius r centered at the point z0, it's a little bit hard to read, so this is the z0 right here. In that disk, I have convergence. So all the blue shaded regions, I get convergence. Outside of the disk, I get divergence. When I plug in z's from out here, the series diverges. The theorem says nothing about z values on this boundary. It gives us no information. We've seen an example where the series diverges everywhere on the boundary, but all kinds of things can happen on the boundary. And lastly, if I choose a radius little r that's strictly less than big R, then if I look at the circle of radius little r, which is contained in a disk of radius big R, in that little disk I get uniform convergence. We call this uppercase R, the radius of the big disk, the radius of convergence of the power series. And you've probably heard of the radius of convergence before when you studied series on the real line. And the word radius made very little sense because you got an interval of convergence and not a disk. Now the word radius makes sense because it's the radius of a disk. We found that a power series converges for z values from a disk and diverges outside of the disk. This is called the disk of convergence, and its radius is the radius of convergence. Let's look at some examples. We already looked at the power series of the z to the k's, and we saw it converges when the absolute value of z is less than 1, and diverges when the absolute value of z is bigger than 1, therefore the radius of convergence is equal to 1. We also looked at this power series, minus 1 to the k over 2 to the k times z to the 2k, and we found that converges when the absolute value of z is less than root 2 and diverges when it's greater than root 2, and therefore root 2 is the radius of convergence of this power series. Next, let's look at the power series k from 0 to infinity, k to the k, z to the k. So these k to the k's, those are my ak's. If I wanted to write out a few terms of this series, when k is equal to 0, 0 to the 0th power by definition is 1, so I get 1 times z to the 0, which is 1. When k is equal to 1, I get 1 to the first power times z, that's z. When k is equal to 2, I get 2 to the second power, that's 4 times z squared. When k is equal to 3, I get 3 cubed, which is 27 z cubed, and so forth. So the terms, the coefficients in front of the powers of z grow quite rapidly as k gets larger and larger. So for what values of z does this series converge? Well, obviously when z is equal to 0, all the terms are 0. So that's quite obviously a point of convergence. Let's now pick an arbitrary z that's not 0. And we observe the following. If I look at the absolute value of k to the k times z to the k, I can pull this exponent k outside. And I get it's k times the absolute value of z to the power k. But this k times the absolute value of z, notice that z is fixed. I can pick a large enough k, for example, greater than 2 over the absolute value of z, and this term is greater than or equal to 2 to the k, which means the individual terms of my power series, they don't go to 0. But a series whose terms don't go to 0 cannot converge. The terms going to 0 is a necessary, not a sufficient, but a necessary condition for convergence. Since my terms don't go to 0, the series does not converge, and so it can't converge for any z that's non-zero. Therefore, the radius of convergence of this power series is 0. There is no disk around the origin in which the series converges. So this power series has radius of convergence 0. How about if I look at z to the k divided by k to the k? Well, again, let's pick an arbitrary z and observe that the absolute value of z to the k divided by k to the k, I can do the same trick and pull these k's out, is the absolute value of z divided by k to the kth power. Now when I pick a k large enough, for example, bigger than 2 times the absolute value of z, then this term z over k to the k is bounded above by 1/2 to the k. So most of the terms of the power series, except for the first few, are less than 1/2 to the k in absolute value. But the series of 1/2 to the k is a geometric series, and we know that converges. Sum 1/2 to the k from 0 to infinity, it converges, and we actually know what it is. Its sum is 1 over 1 minus 1/2, which is actually 2. So since my absolute values of my series are bounded above by terms that belong to a series that converges, it's a known theorem that therefore the original series converges as well, even in absolute value. So no matter what value of z I choose, eventually for large enough k, this is going to be true. And since finally many terms of a power series do not influence its convergence, we find that this series converges no matter what z I plug in there. Therefore, it converges for all z in the complex plane, and that is an example of where the radius of convergence is infinity. I can choose as large a disk as I want to, and the series will converge inside it. Here is the big theorem that makes power series so powerful. Suppose I'm given the power series and its radius of convergence is r, and I'm going to choose that r is greater than 0, because when the radius of convergence is 0, I only have this one point of convergence, which is a bit boring. And now I look at this function. F of z is given by the sum ak z minus z0 to the k, where z varies. And I let z vary inside the disk of convergence. And the claim is that the outcome is an analytic function in that disk of convergence. And more is true. An analytic function has a derivative, and I can find that derivative by differentiating this series term by term, so I can pull the derivative inside of this infinite sum. We know that we can pull derivatives inside of finite sums, but for an infinite sum, that's a whole different matter. So that's something that needs to be proved, but it can be proved that for this infinite sum, which converges inside the disk of radius r, I can differentiate inside the infinite sum, and therefore find that f prime of z is ak times the derivative of z minus z0 to the k, which is k times z minus z0 to the k minus first power. Notice I started the series at 1 here, because when k is equal to 0, the derivative of that term goes 0 and goes away. The second derivative can be found similarly. I just take another derivative inside, so find ak times k minus 1 times z minus 0 to the k minus 2, and now it suffices to start the sum at 2. In particular, if I look at the nth derivative of f at z, so I keep taking derivative, the nth derivative is going to be something like the sum k from n to infinity, and then here I have ak times k minus 1, and so forth through k minus n plus 1 times z minus z0 to the k minus n. When I plug in z0 for z, right there, that makes this z a z0. So as soon as this power k minus n is at least 1, the term vanishes, because I have 0 to some positive power, which is 0. Only when this exponent is equal to 0 do I get a 1. So when the exponent is equal to 0, that's the case when k is equal to n. So the first term of my power series. The nth derivative of f at z0 is the first term of the power series, and that's going to be an times n minus 1, and so forth, all the way through n minus n, which is 0, and so I just left with a 1. That's the factorial of n. So that's an times n factorial. I wrote this out back here again. The kth derivative, so I've put it in terms of k instead of in terms of n. The kth derivative of f at z0 is ak times k factorial, and I can solve that for ak. ak is therefore the kth derivative of f at z0 divided by k factorial for all k's. So that is amazing. What this says that not only do I get an analytic function inside the disk of convergence, but in fact, these AKs are strongly related to the derivatives of that analytic function, namely the kth derivative of this analytic function at the point z0, the center of the disk, divided by k factorial, is equal to that AK. Let's look at some examples. So remember, the series z to the k has a radius of convergence 1. Therefore, by the theorem, this function f of z given by the sum k equals 0 to infinity z to the k is an analytic function. We kind of knew that. We found what the sum is, right? We know f of z is 1 over 1 minus z. We know an explicit formula, and we know that is analytic. In fact, we know this is actually an analytic function in the whole complex plane minus the value 1. we know this function agrees with the power series in the disk of radius 1, and the theorem says this function is analytic. But it also says I can differentiate term by term. So let's take the derivative and differentiate term by term inside the sum, as the theorem tells us. We find that f prime of z can be found as the sum k equals 1 to infinity k times z to the k minus 1. Often it is desirable to express a power series where the z's are powers of k and not k minus 1. I therefore can do a shift of my summation index. Because the powers of z, when k is equal to 1, I get a power of 0. When k is equal to 2, I get a power of 1. So I have all the powers of z from 0 to infinity here. And therefore I can write this sum in terms of powers of z. And I notice the number in front of z is 1 bigger than the exponent. So that must be k plus 1. This is called a shift of the index. If you wanted to do this in a formal way, you could briefly say, well, let's L be a new index, and let L be k minus 1. So if I replace k with my L, k is L plus 1, and therefore I get the sum, and whenever I see a k, I'm going to write L plus 1. So this k becomes L plus 1 times z to the, and the k minus 1 was my L. Now, since L is k minus 1, if k is equal to 1, L is 0. So L must run from 0 to infinity. So I first rewrite this first series in that way, and then I rename my L back to k, so that the series looks like the one on the right-hand side. So now remember, we also know that f of z is 1 over 1 minus z, and so we know the derivative of 1 over 1 minus z, which is 1 over 1 minus z quantity squared. So I found two ways to express the derivative of the function f. And since both are the derivative of the same function, these two things must agree with each other. And I therefore find that the sum k plus 1 z to the k is 1 over 1 minus z quantity squared. So I was actually able to evaluate a new series and find its value using the fact that the derivative of my power series can be taken term by term. Note, power series can similarly be integrated term by term. How does that go? Suppose you're given the power series of radius of convergence R, then for any W inside this disk of convergence, so here's the disk of convergence of center Z0. For any W in that disk, we have that the integral from Z0 to W of this whole series is equal to pulling the integral inside. So the series AK of the integral z minus z0 to the k, where the integral is taken over any path from z0 to w. It doesn't matter which path I choose, the integral will always give you the same value, because we're talking about an analytic function in a disk. I can actually evaluate this. I have an antiderivative for z minus z0 to the k, namely 1 over k plus 1 times z minus z0 to the k plus 1. And then you need to evaluate that from z0 to w. When I do that, when I plug in z0, it's nothing. When I plug in w, I get 1 over k plus 1 times w minus z0 to the k plus 1. Let's apply this theorem again to our power series z to the k, which we know has radius of convergence r equals 1. So for any w whose absolute value is less than 1, we can therefore integrate this power series from 0 to w, or again by that integral, we mean the integral over any path from 0 to w within the disk. And we find by this previous fact that the integral from 0 to w of the series z to the k can be found by pulling the integral to the inside. Therefore, it's the series of the integral from 0 to w of z to the k dz. But z to the k has an antiderivative in the disk where this path is located, and the antiderivative is 1 over k plus 1 z to the k plus 1. If we evaluate the antiderivative at the two bounds, we find 1 over k plus 1 times w to the k plus 1 minus the antiderivative at 0, which is 0. And we therefore find that the original integral of the power series is equal to the series of 1 over k plus 1 w to the k plus 1. We can now do a shift of the index of summation again, as we did on the previous page. We notice we're summing from k equals 0 to infinity, but if we look at these exponents here of w, they start at 1, then 2, then 3, all the way through infinity, and that 1 over k plus 1 is the exact same number. We could therefore simply sum from 1 to infinity and call the exponent k instead of k plus 1, and we'll then be dividing by k. Furthermore, we also know that the sum of the z to the k's is 1 over 1 minus z, as long as the absolute value of z is less than 1, of course. And therefore, instead of integrating the whole series as we did above, we could just as well integrate the function 1 over 1 minus z. Well, an antiderivative of 1 over 1 minus z in the disk of radius 1 centered at the origin is minus log of 1 minus z, because the derivative of minus log of 1 minus z is minus 1 over 1 minus z times the derivative of the inside function, which gets rid of that minus sign. So the derivative of minus log of 1 minus z is indeed 1 over 1 minus z. And if I again plug in the upper bound w, I get minus log of 1 minus w, and at the lower bound the primitive is equal to 0. We used here that the logarithm of 1 minus z is analytic in this disk. So let me remind you why that is the case. The logarithm function itself was analytic in the complex plane minus the negative real axis. So that's where log z is analytic. Now we're looking at logarithm of 1 minus z, which shifts this region to the complex plane minus the portion of the positive real axis starting at 1. So that's where log of 1 minus z is analytic, or also minus log of 1 minus z. That doesn't change that minus sign. And therefore, in particular, it's analytic in this disk of radius 1 centered at the origin. That's where we're interested in. That's where our path is located. That's why minus log of 1 minus z forms a primitive of 1 over 1 minus z in that disk. So we have shown that the integral from 0 to w of the power series c to the k is equal to the power series k from 1 to infinity of w to the k over k. But we've also shown that the same integral is equal to minus log of 1 minus w. Since both of these functions are equal to the integral of the original power series, the two right-hand sides must agree. So it must be the case that the sum k from 1 to infinity w to the k over k is equal to minus log of 1 minus w. We've therefore found a power series expansion for the logarithm function. Now log of 1 minus w, that sounds a little awkward, so let's set z equal to 1 minus w. In other words, replace this and call this actually equal to z. And then we're going to bring this negative sign to the other side and find a nicer way of writing this formula as log of z is equal to minus, that's the minus sign that came over, sum k from 1 to infinity. And if z is equal to 1 minus w, then w is equal to 1 minus z. So we find 1 minus z to the power k divided by k. And typically, if you write a power series, you want it in the form z minus z0, not z0 minus z. So our z0 is equal to 1, but we want to interchange these two terms here. If I interchange these two terms, I have to pull out a negative sign. So I get a minus 1 to the k, and I also pull this negative sign inside of the sum. So I find minus 1 to the k plus 1 divided by k times z minus 1 to the power k. So this is a power series for log of z. In the disk of radius 1 centered at 1. So the disk of radius 1 centered at 1 is this disk right there. And in this disk, I have that this is true. I have a power series that is equal to the logarithm function there. Let's write down the first few terms. When k is equal to 1, I find minus 1 squared, that's 1, divided by 1, times z minus 1 to the first power. So the first term is z minus 1. The next term is minus 1 cubed divided by 2, so minus z minus 1 squared over 2. Next I get the plus z minus 1 cubed over 3, and so forth. So it seems quite important to find out where a power series converges. And we've looked at some examples and found in our examples the radius of convergence of the power series. How would you find it in general, though? If I'm giving you an arbitrary power series, how would you determine its radius of convergence? That's a question we're going to deal with in the next lecture.